This is number 2 for AP FRQ particle motion non-calculator. Let's read the problem here. Two particles move along the x-axis for time interval between 0 and 8. Position of particle P at time t is given by x of t, while the velocity of another particle Q is given by v of t. Particle Q is at position x equals 5 at time t equals 0, so we can say x of 0 is equal to 5. So we have two particles, but one particle is in the position form and the other particle is in the velocity form. Okay, keep that in mind. So for A, when is the particle P moving to the left? Well, if we want to figure out when the particle is moving to the left, we want to know information about the velocity, find critical values for the velocity, create our velocity sign line, and test our intervals. We want to first know when the velocity of the particle is 0 before we can go and decide when it's moving left and when it's moving right. So first thing is we're going to have to find our velocity function. So we're dealing with with particle P, and we're still sitting at the position form, so we have to get from position to velocity, and to do that we're going to find the derivative. So again, we're going to find the velocity function, we're going to find our critical points, we're going to create sign line, and then we're going to test intervals. So the derivative formula for natural log of u is going to be u prime over u. So the derivative for our u value is going to be everything inside the parentheses. So the derivative of t squared minus 2t plus 10 is simply 2t minus 2 all over the full expression inside the parentheses. And now we're going to be looking for critical points. So I can factor the numerator, take a t2 out of the numerator, I get 2 parentheses t minus 1. But the denominator doesn't factor, and I don't have any critical points from the denominator. We know that we're starting at 0, and we're going to 8. So for my velocity sign line, I can have my starting and ending point, and my critical value is going to be at 1 because that is what I get when I set my numerator equal to 0. I get t minus 1 is equal to 1. T minus 1 is equal to 0, and therefore t is equal to 1. We're going to test each interval here, so a value that we can choose between 0 and 1 is 1/2. I can plug 1/2 into my velocity function, so I will get a negative over a positive. Negative over positive, that's going to be negative. And if I plug in 2, which is a value that I can choose between 1 and 8, the numerator will give me positive, the denominator will also give me positive. So we get positive over positive, which is positive. So negative velocity means moving left, positive velocity means moving right. So our particle moves from 0 to 1. And here's something we got to be careful about, is that at 0, it doesn't guarantee that the particle is not moving. So if I plug 0 into the velocity function, I'm not going to get 0. If I plug 0 in, I'm going to get a negative over a positive, which is negative. So that means at 0, this particle is already moving. The particle is already moving at 0. So we need to include that as part of our domain, or as part of our interval. So bracket 0 to 1, since velocity is less than 0, or since velocity is negative. So part B, for time intervals from 0 to 8, find all the times where the two particles travel in the same direction. Well, we have the velocity sign line for our first particle, so that's something that we can use. But let's find the velocity sign line for the second particle. This is a different object traveling with its own rule. So this is already in the velocity form, so we can just go ahead and find those critical points. And the same steps: find critical points, create sign line, test intervals. So no need to find the derivative. We can just go directly into setting this equal to 0. We can factor this out. Multiplies to be 15, adds up to be negative 8. We have negative 5 and negative 3. We solve for t, we get 3 and 5. We place them onto our sign line along with 0 and 8 being our endpoints. and I can plug 1 into the velocity function to the factor form of the velocity function. I get 1 minus 5 and 1 minus 3. 2 negatives gives me positive. Plug 4 in. 4 falls between 3 and 5. 4 minus 5 times 4 minus 3, that's negative times positive, which is negative. Plug in 6 finally. Positive times positive, which is positive. So if I line these two sign lines up, I'm looking for when the particles are moving in the same direction, so I'm looking for the same signs. I see same signs in the interval from 1 to 3, though these are both positive velocities. And there's also, looks like the negatives are not matching up, but there's another interval where I'm going to get positive velocity, so 5 to 8 here. Okay. So it doesn't have to be positive velocity, it just so happens that these are the only time intervals that we have the same signs. Okay. Part C, find the acceleration of particle Q at time t equals 2. So we're back to Q. We're going to find the acceleration function. So let's find the derivative using power rule. T squared becomes 2t, 8t becomes 8. So we want to know, is the speed of the particle increasing or decreasing? So speed of the particle is dependent on comparing the signs between velocity and acceleration. If there are same signs between velocity and acceleration, then the speed is increasing. If there are opposite signs between velocity and acceleration, then we have decreasing speed. So we have velocity and acceleration available for us to use. So we'll evaluate velocity and acceleration at time t equals 2. So velocity at 2 is going to be a positive value, which is 3. I'm going to plug 2 into the acceleration function. I get 4 minus 8, which is negative. So I have negative and positive. These are opposite signs. Opposite signs between velocity and acceleration indicates that speed of the particle is going to be decreasing. Okay, part D, find the position of particle Q the first time it changes direction. So let's create a position function for particle Q. So particle Q, we can take the antiderivative, okay, move it up to the position function, or we can think of it as final position equals initial plus displacement. We can take the antiderivative, but we're going from 0 to 3. Particle Q first changes direction at 3, so we know that is going to be the endpoint that we're going to be using. So our final position is initial plus displacement, so my final position at 3 is my initial plus however much I travel in that time interval. So x of 0 is 5, that's given to us at the beginning. And then we can take the definite integral here. We can work this out by hand. This is non-calculator, so we have to go through this by hand. Make sure that we go through, we anti-differentiate first. So we go through power rule. T squared becomes t cubed over 3. 8t becomes 8t squared over 2. 15 becomes 15t. Half bracket to indicate that we're ready for our bounds. Upper bound gets plugged in first, so 3 gets plugged into all the t values. Minus parentheses, the 0. And 0 is going to take out all the terms. Again, be careful with 0. In this case, 0 does wipe all these terms out, but not in every case, in every problem, do 0 necessarily take everything out. So just be careful. Confirm that 0 gives you 0, or if it doesn't, that you're taking the time to plug in. So all these gives us 9 minus 36 plus 45. That's the displacement, plus our starting position of 5. And we're going to be able to know where we end up at t equals 3, and we end up at position 23.